So we're about to reach the end of our lessons on stoichiometry at the high school level. What we're going to do today is merely practice. So this is the last lesson in our stoichiometry series. So yesterday's practice homework problem was, if 2.50 grams of iron is placed in an aqueous solution containing 25 grams of antimony 3 chlorate and 3 grams of antimony metal is collected, what is the percent yield? So we're going to start with balancing the equation. That's what I'm going to start with. You don't actually have to start with balancing an equation. You can actually start by setting up your stoichiometry. And then when you get to the point where you need a molar ratio, then do your balanced equation. That's perfectly okay. But what we're going to do is start with the balanced equation. No, the balanced chemical equation is when you'll have iron and antimony 3 chlorate, and then it's a chemical equation we're talking about. There is an equation that is stoichiometry. You're right. Okay? But usually when I refer to the equation, I'm talking about a chemical equation. I see your point as far as, why that would lead you to some confusion. All right, so we had iron. And iron is a metal, and all metals that are by themselves except for mercury are going to be solids. Putting that in a solution that has antimony 3 chlorate. Antimony is Sb. Chlorate is ClO3. Antimony, Roman numeral 3, means this has a 3 plus charge. The chlorate ion has a 1 negative charge. So to balance this formula, we need 3 chlorates. All chlorate compounds are always soluble, so we're going to show this from being aqueous. Then on the other side, what we're going to do is we're going to look for what is the most likely kind of reaction that's going to occur. This is classifying the reaction. Since we have a metal by itself and we have a metal in this compound, we would assume there would be a single replacement reaction. Metals can replace other metals, or metals can replace hydrogen ions in an acid if they're more active. I realize that antimony didn't show up on your standard reduction potentials, and so you had to go to the activity series to find antimony was less active. Although the question actually tells you there's going to be a reaction. You can't produce antimony without iron being more active than antimony. But I won't give you one like that on the test. I'll make sure there's not one on the test that's that way. So iron displaces antimony. That means antimony's by itself over here, and metals by themselves, solids. Iron's going to join up with the chlorate. We need to figure out which form of iron we're going to have, because iron has 2 potential oxidation numbers, and therefore 2 potential ions. Iron 2 is more active than iron 3, so what you're going to likely form here is iron 2. I mean, it's the most likely one to form when you're running a single replacement reaction, because iron 2 is more active. So to balance this equation, we just subscript 2 here. Excuse me. Chlorate compounds are always soluble, so this is aqueous, since this is taking place in water. Now we're ready to balance the equation. We're going to list our elements here: Fe, then Sb, then Cl and O, iron, antimony, chlorine, and oxygen. Now you should be able to grade this as you go along, because you already know all the things I'm looking for here, okay? Elemental symbols, physical states, operators, polyatomic ions are all worth 1 point each. So as you go along, you can count what's right and wrong here. We'll go through later and figure out how many points, okay? All right, so we have 1 iron here, 1 antimony. This 3 outside the parentheses means I have 3 chlorate ions, and the chlorate ions have 1 chlorine. So that means I have 3 chlorines, and I have 9 oxygens. Over on the right-hand side at the moment, I have 1 iron, 1 antimony. I've got 2 chlorines here, and 6 oxygens. So to balance the equation, we can only use coefficients. We can't mess with the formulas. These formulas are all set. You can't stick subscripts in there or any numbers in the formula anywhere. You can only use coefficients in front of each of the species, which changes the number of the atoms for everything in that species. So let's see, we're going to leave oxygen for last. We're going to have to start with chlorine. Since I have 3 on the left and 2 on the right, and they come from these two species here, the only way to get this balanced is to put a 2 here and a 3 here. Now over here, that's going to change the number of antimonies and chlorines and oxygens, and over on this side, it's going to change the number of irons and chlorines and oxygens. So I can see now that I have 2 antimonies. So I had 3 times 1 chlorines in the formula, now times 2, that's 6 chlorines. 3 times 3 oxygens in the formula, now times 2, that's 18. Over on this side, I now have 3 irons. I had 1 chlorine in this chlorate formula inside the parentheses. The 2 outside multiplies by 2. That's 2 times this 3 now gives me 6 chlorines. And I had 3 oxygens in the chlorate formula, then times this 2, and now times this 3. So 3 times 2 is 6, times 3 is 18. So we want to try to get our irons and antimonies balanced. A coefficient 3 in front of this will fix the balance on the iron, and a coefficient of 2 in front of antimony will fix the number of antimony. So now we have a balanced equation, and we need that for any kind of stoichiometry, because stoichiometry requires a molar ratio step, and we get the molar ratio step from these coefficients. Now we're ready to do this stoichiometry to try and find the limiting reactant. This is going to be mass-to-mass stoichiometry because everything in the problem is in terms of mass. I'm just going to start with 2.50 grams of iron. Doesn't matter. You could start with, 25 grams of antimony. You would have gotten a different numerical answer, but it would have reached the correct conclusion either way if you follow the procedures I've given you. So we're going to put 2.50 grams of iron on the top of a fraction over 1. Always put starting amounts when we're doing stoichiometry over 1. Then we need a molar mass ratio here, a molar mass, in order to convert grams into moles. You've got to go through a molar ratio step to go from one species to another, so you've got to get this into moles. Whatever you're starting with has to be converted to moles to go from one species to another. So iron's atomic mass on the periodic table that you're allowed to use in this class is 55.85. We're only looking at the number of irons in the formula. Well, in this case, it's just 1. So we don't even have to multiply by 1 here. It's just that number is the atomic mass if we write it in grams. So we're going to say this many grams of iron is equal to 1 mole of iron. Okay, this equality statement is required in this class because I found over the years that it really helps students to reinforce where we're getting the 2 parts of the conversion ratio, the conversion factor here, the conversion unit. So I'm going to put the matching units of measurement and species on the bottom, matching what's here in the previous part of the problem. So 55.85 grams of Fe, and then 1 mole goes on the top. By building this conversion unit this way, I've got 2 things that are equal, put it into a fraction. The value of this fraction is 1, so that when we multiply here, we're actually changing the way we're measuring it without actually changing the amount. So we're going to cancel units, just like you cancel x's and y's in algebra, and species we're canceling. And we have things in moles. I'm not going to do the math on that yet. I'm going to go through all the steps here to get to the answer I need. So now we're ready for that molar ratio step. We've got this in moles. Now we're ready to convert from this species to the species we're looking for. And right now we're trying to find the limiting reactant. Iron and antimony 3-chlorate are the reactants. So we're going to put antimony 3-chlorate on the top here. So that's 2 moles. So these coefficients here can mean this many formula units, but it can also mean the number of moles if we just multiply everything by Avogadro's number. So now we can cancel out units of measurement and the species, and we're successfully at the moles of this new species. So we need a molar mass ratio. We've got to calculate the molar mass for antimony 3-chlorate. So we have to write down the elements here just so we can keep up with everything. Sometimes there's so much going on, it's hard to keep up with everything. The atomic mass on your periodic table for this class for antimony is 121.76, and the formula, just the formula, not the coefficient, just the formula, there's 1 antimony. There's 3 chlorines, and the atomic mass for chlorine on your periodic table is 35.45. So we're going to multiply that by 3, and there's 9 oxygens, and that has an atomic mass of 16.00 to be more exact, because you have to keep up with those significant digits. So now we're going to multiply across and then add everything together. What we're really doing is adding up all of the atomic masses of all the atoms in the formula, and that is the atomic mass, only we write it in grams. I'm sorry, not the atomic mass. That is the molar mass, and that is the definition of molar mass, the sum of all the atomic masses of all the atoms in a formula. So this times 1 is 121.76, then 106.35, and 144.00. Now I know when you put in your calculator is going to show you 144. You have to be smart enough to know, well, those 2 zeros there, those are significant. I've got to have 2 zeros here. Add all that together, we get 372.11. There are no empty slots over here, so there's no rounding off to be done in this. So we're going to do add our units of measurement and the species, antimony 3-chlorate, and show that equal to 1 mole of antimony 3-chlorate. And we have a molar mass equality statement to build a molar mass conversion unit up here. I have moles of antimony 3-chlorate here, so I want moles of antimony 3-chlorate here. And this side of the equality statement is the side I want on the bottom. And then I want the other side on the top, this will end up giving me my answer in grams, which I need to compare to find out what the limiting reactant is. And I'll show you that in a second. I can cancel units now of moles and the species antimony 3-chlorate. And I'm ready to do the math for this problem. And put it in your calculator. You should get 11.10444. And some of you may get more digits or less digits than I'm going to show here. That's fine. Just put down what your calculator shows. And this is grams of antimony 3-chlorate. We want to round that off to the correct number of significant digits. We have 3 digits in this number here. It's a measured number. This is a calculated number, and this is a calculated number. So for those numbers, and those are the only ones that matter when we're figuring out significant digits in multiplication and division, this one has the least digits. So we want our final answer to have that many digits, 3 digits, and underline everything else. Draw an arrow to show a rounding off, and I get 11.1 grams of antimony 3-chlorate. All right, now we're going to use this now to figure out what the limiting reactant is. Let's go back. I'm going to go back to the problem. And want to compare that number against the actual amount of antimony 3-chlorate given in the problem. Now, this number right here, this measured number, or this measurement, is the mass of antimony 3-chlorate required to fully react with all this iron over here. Okay? In the problem, it says I have 25 grams of antimony. Am I looking at the right thing? No, wrong problem. Oh, don't I? Find the right problem. Okay. So the problem says I have 25 grams of antimony 3-chlorate. That's way more than this. So I'm going to have some antimony 3-chlorate left over. Therefore, antimony 3-chlorate is the excess reactant. And that means that the other reactant, in this case iron, is the limiting reactant. And that limiting reactant is really key, because once I find the limiting reactant, any calculation is done from this point forward will start with the given amount of limiting reactant. And when I say given amount, If you happen to start with antimony 3-chlorate when you did this calculation here, you don't, well, let me back it up. If this were the limiting reactant, you wouldn't start with this amount. You start with the amount given in the problem. And the amount given in the problem of the limiting reactant, in this case, is 2.50 grams. Okay? So the next problem starts exactly the way we started this problem. We just got lucky here. All right? It might be you're not so lucky and you have to start with something different, but this time it's going to start exactly the same. What we want to find now is the theoretical yield, and we've got to start with the limiting reactant, that happens to be iron. Now, it's always a good idea, just to help you on the test, if you'll go ahead and label these. This is your limiting reactant now. You know it's a limiting reactant. Doesn't hurt to label it, so you won't forget what you're looking for. This is the excess reactant, and the product you're seeking is this one. It wouldn't hurt when you write out your equation and you balance it. Go ahead and label those things in the problem so you won't inadvertently do mass to mass to find this, and that's not what you're looking for in the end. Okay, I've seen a lot of students do that. Trying to give you some tools and tips to help you get to the right answer. All right, so we're going to start the calculation to the theoretical yield, starting with our limiting reactant, 2.50 grams of iron. Put it over 1. Got to convert it to moles, and we already have that step written in the problem above. And now we're getting to the molar ratio step. We're still going to have 3 moles of iron on the bottom from the equation, 3 moles here, but now we're going to this product. So we want to put 2 moles of antimony on the top. Another thing that I see students do sometimes is they want to write shorthand. And instead of writing out the whole formula for antimony 3-chlorate, they'll just write SB. Well, now you're going to confuse that with the product you're looking for. So don't take those kind of shortcuts, okay? Just don't do it. Now, we already know the molar mass of antimony. I'm going to write it out so that I have an equality statement to give me the molar mass ratio I need here. 121.76 grams of antimony equals 1 mole of antimony. Okay, now I require that you write out an equality statement to justify all the conversion units. Please don't forget to do that. 1 mole of antimony and 121.76 grams of antimony. And we're ready to do this math. Okay, I got 3.633542262 grams of antimony. Want to round off? I haven't even canceled units yet. Need to do that. Make sure I've set up the problem properly. I highly recommend you do this as you go along. That way you know where you come, where you're going to. It's easier to keep up with everything. Keeps it all organized, and keeping it organized on complex problems like this is essential. And so we're going to round this off, and we get 3.63. So this is our theoretical yield. I don't need that, just theoretical yield. Alright? Now, percentage yield is actual yield over theoretical yield. Actual yield in the problem is 3 grams of antimony metal. So we're going to put 3 grams of antimony metal, and that's grams, over 3.63 grams of antimony times 100. This parentheses is necessary because it tells you do this operation first before you do this one. And I got 82.64462 0.80992%. Rounded off to the correct number of significant digits, and I also didn't cancel here. In this case, the units of measurement cancel, and the species cancels. A valid percentage will always cancel units. If you set it up and you're not canceling the same units, if you're not able to cancel the units in the appropriate way, then you know you've done something wrong in setting up your percentage. You want to have 3 significant digits, 1, 2, 3, underline everything else, draw an arrow, show the rounding off with that arrow, and we get 82.6% yield in antimony. Okay? For students that didn't earn the kind of grade that they hoped to earn for that homework, here's the makeup. If 15.55 grams of nickel is placed in an aqueous solution containing 25.35 grams of copper 2 chlorate and 12.25 grams of copper metal is collected, what's the percent yield? One last problem now. If 5.55 grams of steel wool, which is iron, is closed in a container with 0.25 liters of oxygen at STP, remember STP is standard temperature and pressure, how much rust will be produced? Remember, rust is Fe sub 2 O sub 3. And then once you find how much Fe2O3 is produced, how much rust is produced, that'll be your theoretical yield. Then you want to find the percent yield if only 0.75 grams of rust is collected.